there's a bit of an air gap. And then what I've drawn in dark blue is this selective coating that you see here. It's a large sheet of aluminum. It's pretty well a 4x8 sheet. That's about the size of the collectors. And then welded to the back of this aluminum is that pipe that zigzags back and forth, and it's a pure copper pipe. Then on our collectors, there's an air gap. They're open at the bottom. It's about 4 inches. This diagonal line is supposed to show the collector is broken here, so it's sorted to scale, except that it's 8 feet tall instead of a couple feet tall that I have here. So air is allowed to come in the bottom of the collector. It'll be heated because it's very hot inside here, and it will rise, but most of the time the top is sealed off by a rubber baffle. The back of the collector for almost all of this 8 feet, except for 4 inches at the top and bottom, has an aluminum wrapped, I think it's a fiberglass insulation. And then I've shown the bottom edge, but also the side edges of this collector have a foam insulation that has been sprayed in there to insulate the collector. So compared to some collectors, like Enerworks makes a commercial version of this exact same one where it's all block solid with insulation. Those ones have less heat loss, but this built-in baffle up here automatically opens when the temperature in the collector reaches 120 degrees Celsius. So that prevents the problem of the glycol solution boiling, which causes pressure problems and also causes acidic problems in the glycol mixture if it boils. So that's a real benefit of these particular collectors at the expense of some performance. So this chart shows the output in watts, which is on the left, versus temperature difference. The temperature difference is TA is the ambient temperature, the outdoor temperature, and TI is the input temperature into the collector, which is typically the coldest temperature in the system that you're trying to heat. So in the picture I showed where there was the water tank with the heat exchanger at the bottom, the glycol coming from the bottom of that heat exchanger is typically the same temperature as the cold water at the bottom of the tank. That's the temperature that will end up going into the collector. So if it's 10 degree water at the bottom of the tank, which is maybe what it comes in from the city, and if it's minus 20 degrees outside, then the 10 degrees minus negative 20 is 30 degrees Celsius. So our collector would be operating, it should be producing about 1400 watts into that water at that time. This blue line is a WSC, the super tube estimation. The curve is a lot flatter because the absorber area of the collector is insulated by a vacuum, which is a really good insulator. But the reason that it starts out so low is that the total area exposed to the sun is a lot smaller on those tubes. And then on those particular tubes, I'm speculating, because they use glass as a conductive material for transferring the heat from the tube to the copper, to the water inside the copper tubing, glass is a relatively good insulator, and I believe that's partly why the initial temperature heat transfer is low. So aside from the collector, you have this energy pack that I had a schematic version of earlier, and this would be the solar storage tank. In this picture, it's a 40 imperial gallon tank, but typically we use a 60 imperial gallon tank. And this is the homeowner's original water heater. And here you can see the hot water comes out of this solar storage tank, and it goes through this U-shaped pipe. This is a heat trap, which prevents hot water from this tank from just going up and back up into the cold water supply. We're trying to prevent that from happening, and that's why that goes here. So on the right is the system exactly as I described. I didn't draw the conventional water heater in this system. I'm not sure if Ron's decided. He'd been talking about electric on-demand water heaters, and he's also talked about electric tank water heaters. But what we've done is taken our base system and added a large 100-liter non-pressurized insulated tank that would sit in the basement of the house once it has one. And we put a coil in the tank. So depending if it's summer or winter. In the winter time, basically when the water in this solar storage tank hits about 30-35 degrees Celsius, this pump will turn on to take heat out of this solar storage tank and put it into the large bulk tank, which is primarily used for space heating. The temperature in this tank is allowed to rise up to about 80 degrees Celsius, which is a maximum safe limit for the tank. Once that happens, this pump will shut off and it will stop transferring heat into this tank. That's also approximately the shut-off temperature for this tank. So if no heat is being taken out of the system and it's a sunny day, both these tanks should end up at 80 degrees Celsius. If it's a questionable day, there probably won't be enough heat for space heating, but we still do the domestic water heating first. And one reason for this is every time you turn a faucet on, a hot water faucet, you're going to end up drawing cold water into the bottom of this tank, which will be in single-digit Celsius, maybe 8 degrees Celsius. That water, because it's so low, is the easiest water in the system to heat. And so that's 8 degrees Celsius is what this solar collector will see in the return line. And so it will be very easy for it to place a large amount of heat into 8 degree Celsius water. Whereas if we didn't have this and we just had a bulk tank, the temperatures would tend to average more over time, and maybe it would be 20 degrees or 30 degrees in this tank. If the floor radiant heat, which I'm going to talk about next, is only capable of reducing the temperature in this tank down to the temperature in the room. So it's very difficult for the temperature of this tank to be reduced much below 20 degrees Celsius. So now I'm going to talk about heat emitters. Historically, hydronic systems worked either on steam, which is basically 100 degrees Celsius, or they worked on hot water, which is typically set to 80 degrees Celsius, which is about 180 degrees Fahrenheit. So that was the temperature of the heat source, and so emitters, which take the heat and deliver it to a room or to heat your air, were typically sized and designed to work with those really high temperatures. But that's one major change with green buildings, green houses. The lower the temperature, the better, and there's a number of reasons for that, which I've tried to list. But one thing to note about these high temperatures is it does work well with forced air systems. So if you're stuck using forced air, you may look at using a higher temperature boiler. And the reason for that is if you have forced air and it's slightly warmer than room temperature but not what you would call hot, it feels like a draft or a breeze and it cools you down rather than heating you up. So low temperature design, why is it better? When everything's at a lower temperature, there'll be less heat loss, less heat wasted. Hotter sources can always be reduced down to lower temperatures. So if you design your emitters or your building to work at a low temperature and somehow you come up in the future or even in the short term with a higher temperature heat source, you can still use it, but the inverse isn't true. If you have a low temperature heat source like solar or geothermal or a condensing boiler, air-to-air heat exchangers, maybe some new state change material that release heat at a lower temperature, none of those will work very well with an old-fashioned heat emitter, like an old style baseboard heat or even in-floor heat that's been designed to work at a higher temperature. Those low temperature sources won't transfer the required amount of heat energy into your room. So in almost all cases, your low temperature emitters need to be considered at the design stage. It's not good enough to say I'm putting in-floor heat in. I'm not sure what my heat source is going to be, but I'll put in-floor heat in now, and you just tell your contractor to install that because they'll probably install it based on what they're used to, which is high temperature boiler heat. And the in-floor tubes will be not spaced appropriately for low temperature heat. And then avoid, I talked about the forced air, avoid putting low temperature heat into forced air systems because it will tend to have a cooling effect.